For this example, we're going to use Newton's law of cooling, which is here. I just pasted this from the text, page 362 in the e-text. And we're told what this formula is. And what I did over here was I just wrote down all of its components, its different variables or constants. So U of T is the temperature U at time T. This capital T is the constant temperature of the surroundings. U sub 0 is the initial temperature. And K is some negative constant. And actually that constant is what we're going to first be looking for when we go to solve this problem up here. Okay, so let's get some space over here so that we can work with this particular problem. So we're told the thermometer reading is 9 degrees Celsius, is brought into a room with a constant temperature of 29 degrees Celsius. If the thermometer reads 17 degrees Celsius after 3 minutes, what will it read after being in the room for 5 minutes and then after in the room for 10 minutes? So these last two times are actually going to be used after we find the complete model for this particular situation. So let's start picking out some of the things that we do know. And notice that not all of these things that we have to tease out of this problem are necessarily given in order. So for instance, the thermometer reading 9 degrees Celsius when it is brought into the room is actually its initial temperature, 9. We're assuming, of course, 9 degrees Celsius. We're measuring in Celsius since everything else is measured in Celsius. That constant temperature, 29 degrees Celsius, is the temperature of the surroundings. So that's going to be that capital T. And if we know that the thermometer reads 17 degrees after 3 minutes, we can write that as U of 3 equals 17. That's what that gives us here. So at time lowercase t, we have U, the temperature is 17. Notice that we still don't have this negative constant. So what we're now going to do is go back to that formula, place all of these values that we do know into the formula, and we're going to solve for K. So that formula again is over here. So U of T at time 3 is 17. And that equals capital T plus, so we'll write here 29 plus U sub 0 minus capital T, that's the initial temp minus the constant temp of the surroundings, so that's going to be 9 minus 29. And that's being multiplied by the constant E raised to the power K times lowercase t. And lowercase t we know to be 3. That was a specific temperature at a specific time that we were given. So at this point, now our goal is to solve this equation for K. It is an exponential equation because it does have a variable now in the exponent that we need to isolate. So I've just moved my screen here so I have more space. And one of the first things I can do is go ahead and subtract these values. That's going to give me plus negative 20 e to the k times 3. Ultimately, my goal is to get just this exponential expression of a base to its exponent isolated first before I do any other things. So the next thing I want to do is subtract 29 from both sides. And by subtracting 29 from both sides, I should have negative 12 equals negative 20 e to the k times 3. Then divide both sides by negative 20. So negative 12 divided by negative 20 would be 0.6 e to the k times 3. At this point, because I've got the exponential part of that equation isolated, now I can use some techniques for solving exponential functions. The particular one I'm going to use is change this to its logarithmic form. So this is a logarithm with a base of e that is equal to its exponent, 3 times k, or k times 3, doesn't matter there. And I'm taking that logarithm base e of 0.6. We do know, though, that log base e is the same thing as natural log. So I can change that here, and then divide both sides by 3. So I get the natural log of 0.6 divided by 3 equals k. And that is an exact value for k. Keep that in mind, because now when I come back to that formula, natural log of 0.6 divided by 3, I want to rewrite this formula with that value of k here, because it is a constant. Any other constants I also want to include in this formula. The other constant is the surrounding temperature. Another constant is the initial temperature. The only things that are changing in this model or in this formula is lowercase t, the time, and u, the temperature at that time. So let's rewrite this formula. I'm going to rewrite the whole thing here first. So I just rewrote that formula here just so I don't have to keep sliding back and forth. But now I'm going to create my model that fits my conditions. The surrounding temperature stays constant, so I can place that value into this formula. The initial temperature stays constant, so again I can place that value into this formula. I've solved for this negative constant k. Remember that was down here. Natural log of 0.6 divided by 3. But lowercase t does not remain constant in this formula. This is a function of lowercase t, time. So I want to leave that as that variable lowercase t. I can clean it up just a little bit. I can go ahead and say, okay, this is the same thing as plus negative 20 e. I'm still going to leave k as its exact value. I could come into the calculator and get a decimal approximation, but if you choose to do that, just make sure that you're writing down several digits, more than just 2 or 3 digits here, into that decimal. I would probably write down every single one just to maintain as much accuracy as possible. Okay, that part is only the model for this situation described here. Now we've got to find what is the temperature in the room, or on the thermometer rather, after being in the room for 5 minutes. In other words, find u of 5 given this formula that you just developed, this model that you just developed. So we'll replace lowercase t with 5. Now let's see what that looks like in the calculator. So I could do this here just on the calculator screen, on the home screen. 20, I'm just going to go ahead and say minus, since plus a negative is the same thing as subtracting there. And we have e, base e, so I can access that by doing second and then the natural log key. In the exponent, I have a fraction, so I'm going to use the fraction shortcut, alpha y equals enter. So I can type in here the natural log of 0.6 over 3. And that is being multiplied by time t, 5. Notice that it still is in the exponent. That's really important. If you don't have this math type turned on, then you would need to add another set of parentheses to that exponent. So what that gives us is that at time 5 minutes, this thermometer is reading approximately 20.46 degrees Celsius temperature on that thermometer. 20.46 degrees Celsius. Let me make sure I just said that right. Okay, I could do the same thing again for the next part of the problem, which was time 10. Let me just go back and make sure. Yes, for 10 minutes. But instead of rewriting the whole thing again, I'm going to use my shortcut feature, second enter, and then just scroll back into that expression and replace the 5 with a 10. So after 10 minutes, the thermometer reads 25.36 degrees Celsius. These are actually the answers to the question that is being asked. But again, notice that you first had to find this model given your values of your particular situation.